I'll be going over the first paper, Modeling Physics, for OCR Physics A for May 2023 series. So let's get started with the multiple choice. For the first question, we are given which row only contains scalar quantities. So the first one is out because displacement and moment are vectors. Second one is out as all of them are vectors. And for C, well, gravitational potential isn't a vector, and neither is kinetic energy nor mass. So C is the answer. For question number 2, we are given that forces are applied to a circular shaft of diameter d. Which one gives you a correct representation of the torque? With the magnitude Fd. So the answer to this will be B, because torque is basically the force applied multiplied by the distance between the two forces. So that's going to be the diameter, so it's going to be B. Question number 3. We have been given that the resultant force acting on a moving object is 0. So that means acceleration is 0. Which graph shows this? Okay, so we know that if acceleration is 0, it's got to have a constant, gradient. And A will be the answer because over here, dv over dt is basically 0 because v is obviously dx over dt, okay, and that is the gradient of this line. But then when you talk about the gradient of a line which is straight and not a curve, then that itself will be equal to 0, and that would therefore be A will be the answer here. Question number 4. Which row in the table correctly identifies the elastic limit, fracture point, and ultimate tensile strength? Well, P is the elastic limit, and Q is the ultimate tensile strength, and R is the fracture point. So B will be the answer here. Then we have question number 5, which says a wire of cross-sectional area 3.9 times 10 to the minus 6 meters squared carries a load of 240 newtons and the strain in the wire is 0.3%. Which value of Young modulus in Pascal to an appropriate number of significant figure is correct here. So Young modulus is given by stress over strain, or force over area divided by strain, and we know force of 240 over the area of 3.9 times 10 to the minus 6 divided by 0.3%, and that ends up giving us 2.1 times 10 to the 10 up to 2 significant figures, as the rest of the values are also up to 2 significant figures. D is the correct option. Question number 6. We've been given a tennis ball which is hit with a racket, and the graph shows the force the ball exerts on the racket and what is the magnitude of the change in momentum of the ball. So we know that change in momentum is the impulse, or force times delta t, and that would essentially be, in this case, area under the graph, so which is a trapezium. So I'm just gonna break this down to find out what that top length is, and that value is 10 and that is 80, so we have 70 over here. So the area is going to be half 70 plus 100 milliseconds, of course, so times it by 10 to the minus 3, and the height is 45 newtons. Okay, lovely. So that gives us B as the answer. All right, let's move on to number 7. We've been given 2 identical spheres, each of mass 8,700 kilograms, and they are 3.6 meters apart from their centers. And what is the magnitude of the gravitational force exerted on each other? So that's, I think, one of the easiest questions I've ever seen on gravitational forces. We know F is equal to G m1 m2 over r squared, and once you put all the values in the calculator, the distance of 3.6 meters, it will give you B as the answer. Question number 8. It says a particle of mass m and moving at a velocity u collides elastically with the stationary particle q, of also mass m, and then after the collision they both move in those particular directions. And we need to figure out which of these equations is, which of the following equations is or are correct. So let's just break down the components of velocity first into the y-axis and the x-axis. So you would have, for v, you're going to have one like so. This will be v sine theta, v cos theta. Similarly for the other one, just do it in another color, it will be this way as well. So this will be w, and because this is 90 minus theta, it would be, I can just put it down as w. This is over here 90 minus theta, and like so there would be, so essentially that's theta. So this will be w cos theta, and this will be w sine theta. You can use equivalent as well if you want. U is going to be equal to v cos theta plus w sine theta. So number 1 is incorrect therefore. Number 2, well, along the y-axis we don't have any initial velocity. So that means that v sine theta is equal to w cos theta. Of course, you can talk in terms of momentum as well. That's fine too, but m cancels out because they are the same. That's basically correct. And then finally, you have u squared equals w squared plus v squared. So that's also correct actually, because if I just get rid of these forces around here, we know that the direction of initial velocity was along the x-axis. And that is actually the hypotenuse of this right angle triangle that you see around here with velocity v and w. So number 3 is also going to be correct. So my answer would be option number C. Okay, question number 9. We are given during the cold weather salt is spread on roads causing ice to melt without the change in its temperature, and that is basically latent heat of fusion or melting. And which statement correctly describes the energy of the water particles during this process? Whenever we are concerned with latent heat, the only change that happens is the potential energy, and that rises. So D is the answer. Question number 10. An experiment is carried out to estimate the value of absolute zero using the variation of gas pressure with temperature. And we've been given the following apparatus. Which variable must be controlled during the experiment? Well, it's the volume, because PV equals nRT. And if we are analyzing pressure with temperature, we need to keep volume as a control. So C is the answer. Question number 11. A satellite is in geostationary orbit. Okay, so time period, as we know, is 24 hours, just in case. Above 36,000 kilometers above the Earth's surface, and the radius of the Earth is 6,400 kilometers. At what speed is the satellite moving relative to Earth? So we know that V equals 2 pi r over t. And because it's a geostationary satellite, it will have the same time period as that of our Earth. And so it would just be 2 pi times r, and it would be 42,400. I'm going to leave it in kilometers, and divide it by the time period in seconds. So that ends up giving me 3.08, or D as the answer. Question number 12. We've been given 4 oscillatory systems like so. And the question says, which one of them is most heavily damped, where F0 is the frequency. It's well, the natural frequency, basically. So the most heavily damped will be where the amplitude will be the lowest. So D is the answer. Right, let's move on to number 13. During the evolution of the universe, there was a period of inflation. Which forms of matter, if any, existed? 10 to the minus 10 seconds after the Big Bang. Well, we don't have any evidence that any of these particles existed. So we go for C, none. Okay, question number 14. We have been given a part of the emission spectrum for hydrogen in a lab, and all the wavelengths are in nanometers. Which diagram shows the corresponding part of an absorption spectrum? So that means these two are out because these are emission. And then, well, for a galaxy that is moving away from us at that speed. Okay, so that is the comparable to the speed of light. So this is Doppler effect. And what we can see is there's a change in the wavelength as it's red shifted. Okay, it's shifting towards this side in each case, as you can see. So in order to work out that, well, wavelength shift, we need to work out the change in wavelength first. So delta lambda over lambda equals V over C. So 0.031 C over C. In other words, delta lambda over lambda is equal to 0.031. And if I wanted to work out delta lambda, and for all these, well, for C and D, the shift from 434 is to 447. So I'm not going to work that one out because it's quite obvious. In fact, in all of them, it's 447. I'm going to work it out for 486. So I'm going to multiply that by 486. And I am going to end up getting, let's see. Okay, so 15.066 nanometers of shift. And if I just add on the value of 486 to it, I end up basically exceeding, so 486, that would be 501, and that is not being covered in the spectrum that we have, so it would have gone beyond the spectrum over here. So C would be my answer. Okay, so question number 15, we've been given the Hubble constant, and we have to find out the best estimate for it in per second, and 1 parsec is given to us. So 500 kilometers. First of all, let's get that out into meters. So meters per second. And then megaparsec, watch out, is per megaparsec. It's not multiplied. So you have to divide it by 3.1 times 10 to the 16. And because it's mega, we have 10 to the power of 6 to convert that back into parsec. So that will give me B as my answer. Okay, so that's the end of multiple choice. Let's get into section B for the long answer questions. Question number 16 says that the diagram shows a road where vehicles travel at high speeds. We've been given that the marking between the 2 points is 40 meters. The maximum speed vehicles travel at on the road is 110 kilometers per hour. We've been given the table with some speed, braking distance, and stopping distances. Calculate the maximum speed V of the vehicles on the road in SI units. So that's easy. 110 converted into meters by timesing it by 1,000, and then divide it into 3,600 seconds, and that will give me a value of 31 meters per second. A vehicle passes over one of the markings. Calculate the time taken to travel the 40 meters distance between the two markings. So this is time equals distance divided by speed, and that would be equal to 1.3 seconds. Using the table, explain why having markings 40 meters apart helps prevent the collisions. So, well, the braking distance is 75 and the stopping distance is 96. So that means that the thinking distance, 96 minus 75 is 21. So, for the thinking distance being less than 21 meters and braking distance being 75 meters, which is less than 80 meters, as the drivers are, advised to keep a distance of at least 2 markings. So the car would be able to stop even if it was traveling at maximum speed limit. Okay. A vehicle with mass 1600 kilograms is traveling at 110 kilometers per hour. The driver sees an obstruction and applies the brakes to bring the vehicle to rest in 5.6 seconds. Calculate the magnitude of the average resultant force required. So F equals ma, and that is 1600, times by the change in velocity, which is from 31 to 0, but it's just magnitude, so I'm ignoring the negative signs, and dividing it by 5.6 will give me 8857, but seems like rounding to 2 significant figures will be ideal, so 8900 newtons. Explain the effect on the distance required to bring the vehicle to rest if the road has an upward slope. So if the road has an upward slope, we will have a component of the weight acting downwards with respect to the angular components, as it is theta degrees, let's just say. So W equals mg sine theta would resist the upward motion, so the resultant force in the downward direction would increase, and so it would decelerate much quicker, and hence the distance would be smaller for the same amount of work done. Okay, question number 17. The diagram below shows a fairground ride. Each rider is secured in a seat suspended by a rod, and the distance from the top of the rod to the base of the seat is 11.1 meters. And the disc, so the rod is attached to the edge of a disc of diameter 7.8 meters. To test the equipment, a sandbag is attached to the seat and the ride is started. The combined mass of the seat and the sandbag is 12 kilograms. The rod makes an angle of 35 degrees with the vertical. Draw an arrow labeled T on the diagram to represent the tension in the rod. So that would just be along the rod, like so, and like so as well. So I'm just going to draw 2 arrows, although one is sufficient. It will be the same on the other side as well. So show that the radius of the circular path followed by the sandbag is about 10 meters. So for this, you just have to think about the distances along the circle. So if you just notice, first of all, the distance from here to the center is essentially 3.9 meters, as that's the radius. So what we want to calculate is the distance that the sandbag makes, okay, which is further out than 3.9 meters. So I can just use a triangle, a right angle triangle, to work this out. And I know that this rod is 11.1 meters long. I know the angle it makes is 35 degrees. And if I just want to work out this distance, I can then use SOHCAHTOA. So x is equal to 11.1 times by sine 35 degrees, and that gives me 6.37 meters. And so now if I add that onto the distance of 3.9, the total radius is going to be equal to 10.3 meters, and so that is about 10 meters. So we're good to move on now. Calculate the tension T in the rod. Okay, so for T, I'm just gonna get rid of this over here. So let's just resolve our forces. For the sandbag, we have a component of the tension that's acting up and the weight of the sandbag that's acting down. So the component of the tension acting up is T, cos of 35, as it's sort of right like this. So this is 35 degrees, and so it'll be T cos 35 equals W, and therefore T is equal to mg over cos of 35 degrees. M is 12, so 12 times 9.81 over cos 35 ends up giving me 140 newtons to two significant figures. Show that the angular velocity of the ride is about 0.8 radians per second. So that's to do with centripetal force. So we know F is equal to m omega squared r. F divided by m over r, m times r square rooted is omega. Now the centripetal force is provided by the horizontal component of the tension, okay, like acting like so. So that is T sine 35. So it would be T sine 35, and I would use my unrounded values, 12 times 10.3, and square root the answer, and I end up getting 0.82. Part B. When the seat is attached at its highest point, the sandbag is 17 meters above the ground. It is released from the seat to model an object being dropped by a rider. Calculate the time it takes to reach the ground. So it's basically horizontal projection, as the sandbag is going around in a horizontal circle. It travels a distance of 17 meters downwards. So I'm going to use SUVAT S equals ut plus half gt squared, and over here u is 0, and because the sandbag isn't moving with respect to the seat, okay, so u is 0, so t is basically 2s over g square rooted, so 2 times 17 over 9.8, 1, and that gives me an answer of 1.9 seconds. Then for part II, you have to use your answer to AIV, determine the horizontal displacement S traveled by the sandbag before it reaches the ground. So we need to work out this distance, and that is based on the horizontal velocity. Okay, so I can say that x, if this is x, or sx if you want to call it, okay, is equal to ux times t, which is given by the circular speed, okay, the angular velocity basically. So omega r times t. So omega is 0.82, r is 10.3, and t is 1.86 I'm using as unrounded values, and that gives me 16 meters for the answer. For next part, it says determine with reasons the effect on the horizontal displacement traveled if the object released from the rider was a shoe from a rider. So because we are dealing with a shoe rather than a particle, we are assuming that there will be air resistance now. Okay, so this air resistance will basically slow down the shoe or decelerate the shoe horizontally. So the distance it would travel will be smaller horizontally as well. Now there are other options as well for this one, so do check out the mark scheme, as I can't put down every single bullet point, but it gives you lots of different options for this particular part. Right, let's move on to our next question, number 18. In question number 18, it says that a student is attempting to determine the value of G, and the two methods have been described as the vertical drop method, where you have to measure the time of fall of a small dense ball being dropped from rest from different heights. And method 2 is where you have the rolling ball method, where the student is measuring the time it takes for the same ball to roll a set distance down a ramp at different angles. So single sets of results have been shown below, and the times were measured using a standard stopwatch operated by the student. Okay, so there's going to be reaction time. Now compare and discuss the uncertainties of the two values of G and that could be obtained using these single measurements, and describe how the student would analyze both the sets of data with a full range of results that have been taken. So I'm going to discuss this in detail, and I'll put a link in the description box for the written answer. So one thing we have to realize about this question is it's not asking us to calculate the values of G. It's just asking us to work out the, compare and discuss the uncertainties, not even work them out, and then how you would get a full range of results, or rather, how would you analyze them? So let's talk about the first method. So first of all, in comparison, we have a height of 1.20 meters compared to a length of 1.9 meters, which is lower. Okay, the drop height is lower, and the time recorded is also lower than in the second method. So that would just mean a higher percentage uncertainty due to lower values used in the first method. Okay, so in the height, we can say that it's plus or minus 1 centimeters uncertainty, and the length of the ramp is plus or minus 1 millimeters of absolute uncertainty. And in terms of the time taken, we know that, it's good resolution on the stopwatch, but there would be a higher uncertainty due to the reaction times. So that's one thing to consider. Okay, in both cases, because the student is operating it rather than using light gates to record the time. And then we can also look at this angle where there would be uncertainty in measuring this angle. Absolute uncertainty will be about 1 or 2 degrees. Okay, and again, if we were to just generally calculate using the first method, we know that, so for the first method, we will have S equals half GT squared. Now, if we were to consider the value of G, or calculate the uncertainty in G, it would be affected by T squared. So the uncertainty in G will be basically twice due to uncertainty in time, okay, recorded. And that goes to apply in both cases, actually, because we are ultimately using the same ish formula. Now, for the second one, of course, we have this at an angle. So if we have an angle, we have a component of the weight acting at an angle, and that component, or rather just the gravity, it will be G sine theta, as this is G cos theta. So that would be a component to consider. So S will be slightly different in case of calculating the value of value of G. So that will be that. We don't have to calculate it. Okay, so let's not waste too much time discussing about the actual numbers. So uncertainties wise, I think there's one more element of uncertainty, which is the friction, and that is due to the surface of the ramp. There could be friction, which is going to bring in an error, an element of error, basically. So, and also in the second method, it would be difficult to measure the time for the ball to roll down as it is at an angle, compared to the first method, which is just dropping from a simple vertical height. So those are, I think, in comparison, the uncertainties to be considered in the two methods, which I will write down in depth properly. And now that's done, let's talk about the sets of data. So I would, for the first method, I would work on dropping, so first of all, increasing the height, and then dropping it from the same height several times to get an average of the times. Okay, I will use I would use light gates if I am provided with them. So average time, and then thereby changing the heights, I would get the times. So I would end up basically drawing a graph of displacement, or well, height versus t squared, I would get a straight line, and from there I know that the gradient of this line, as per my equation right here, will be, well, it would be, well, gradient times 2 will be the value of g, okay, in the first case. And that will be how I'll get rather better values, value of g, more accurate value. And I should also consider the error bars, considering the line of worst fit to work out the uncertainty in g. So a graph is highly recommended after getting a full range of results. For the second method, I would again get an average value of t for different values of theta, for each value of theta, sorry, and from there I could get, I could just rearrange this equation to work out the value of g as 2 times s over sine theta t squared. So in terms of the second method, it's slightly easier to work out because I'm not really using a graph, but in the first method I think it will give us better results because we are using one. So that's basically that. I hope that helps. I'll write this down and it will be in the description below. Question number 19 says, describe how to find the center of mass of a 2D object, 2D shape, including any equipment required. So you can suspend an object from a point freely near an edge and drop a plumb line and mark on the object, and then suspend the object from another location, not too close to the first one, and then drop a plumb line again, and then mark its position as well. And where the lines meet or intersect is basically where the center of mass is going to lie. Part B says, the bridge can be raised by an electric motor to allow tall ships to pass underneath. And so this is the bridge, and it basically can be rotated up, and when it's in its raised position, it is 14 meters in height. And it says that the moving section of the bridge is 14 meters long and has a weight of 120 kilonewtons, and the center of mass of the structure is 6.3 meters from the pivot. So for the first part, we have to calculate the average power required to raise the bridge to a vertical position in 90 seconds. So we can use power equals energy divided by time, and we know that energy is gravitational potential, energy over here, and mgh, and therefore it will be 120,000 newtons times by 9.8. Actually, that is the weight, isn't it? Yes, sorry. So just 120,000 newtons and times it by the height. Now, it is going to be lifted at the center of mass. It's basically, 6.3 meters from the pivot, and it will be lifted by another 1.3 meters. Okay, so it will basically be a total of 7.6 meters in height. Okay, so that divided by the time, which is 90 seconds, and so it turns out to be 101,000. Okay, 101,000 watts of power. Suggest why the actual electric motor used to lift the bridge has a maximum power output several times larger than that calculated in part BI. Well, that is because the motor may not be 100% efficient. Question number 20A says that we have a sealed container containing n moles of gas, of an ideal gas, with gas pressure P, absolute temperature T, volume V, and the mass of 1 mole of the gas is capital M. So we have to use the ideal gas equation to prove that density of the gas is given by this expression. So we know that pressure times volume is equal to nRT. Now, if I want to introduce density, I have to think about number of moles being written as mass over the molar mass, which is m by capital M. And now, if I just rearrange this slightly to introduce the formula of density, which is mass divided by volume, I'm going to just multiply both the sides by capital M and divide both the sides by V. And there I have my answer. That's replaced by rho and RT, and therefore rho is equal to PM over R times T. Part B. We've been given that an airship has a cabin suspended underneath a gas bag inflated with helium, and the volume of the gas bag is 12,000 meters cube. We've been given the temperature, the pressure, atmospheric pressure, the molar mass, and the volume of the cabin is negligible compared to that of the gas bag. Show that the density of air under the conditions described is about 1.2 kilograms per meter cube. So that's relatively simple. You just have to plug in the numbers into the formula that we just proved. So we have 10 to the power of 5 times 0.029 divided by 8.314 times by 293 kelvins, and then that will give me 1.19 or 1.2 kilograms per meter cube. So two significant figures. Okay, calculate the weight of the air displaced by the airship. So that's just m times g. Okay, and we know that m can be rewritten as rho times v. So we know the density, we know the volume, which is 12,000, and therefore our answer is 140,000 newtons. Okay. Explain why the weight of air displaced by the airship has the same magnitude as the weight of the airship and its contents. So that's because the upthrust is the same as the fluid or, the air, the weight of the air. And as the airship's resultant force is 0, the two forces, the upthrust and the weight, are therefore equal. The pressure of helium in the gas bag is maintained at a value only slightly greater than the atmospheric pressure, suggests why a larger pressure is not used. Well, if there is too much pressure, helium atoms will collide more with the walls and helium therefore may leak out. Part C. The airship engine drives a fan which moves 7.8 kilograms of air per second at a relative speed of 45 meters per second so that the airship starts to move. All the other conditions given in Part B remain the same. Calculate the thrust that the engine produces. So we know that, for a question like this, because I'm given the amount of air per second, I would think in terms of the units. Okay, so if I want to get newtons, I know newtons is essentially kilograms meters per second squared. Okay, so I already have my kilograms per second. Okay, so 7.8 kilograms per second. And if I just times this by 45 meters per second, I end up getting newtons. Okay, so 350 newtons of force is provided by the engine. Part D. The airship has a higher maximum speed at high altitudes, but also produces less thrust from the engine. Explain these observations. Well, as there is reduced frictional forces on the airship, as there is, of course, less density of air at higher altitudes, the resultant force will decrease as the rate of change of momentum reduces. Question number 21. Part A, we've been given a diagram which shows a stationary glider of mass m on an air track. The glider has identical springs with force constant K, which is attached to each end, which are secured to fixed positions or posts. The air track blower is turned on and the glider is displaced a small distance x0, as shown in the diagram. And then we've got the glider, which moves horizontally in a simple harmonic motion. The spring remains in tension throughout the motion. The time taken for 20 complete oscillations is measured and the period t is calculated. Okay, so the relationship between the time period t and the mass of the glider m and the force constant k is described by this particular equation. Show that the equation above is homogeneous by reducing the equation to SI base units. So we know the base units on the left-hand side is just second squared. And the base units on the right-hand side, we're going to have to work out. Pi is obviously unitless. M is kilograms. And you have K, which is spring constant, and that is in newtons per meter. So if I just further reduce this, I would end up getting kilograms meters per second squared per meter, and that cancels out with that, this cancels out with that, and then you have 1 over per second squared, which is the same as second squared. So both the sides are homogeneous in terms of SI units. So for the next part, it says, explain why the magnitude of the resultant force F on the glider is given by F equals 2kx, where x is the displacement at any given time. Well, that's because F on one spring is increased by kx, and the other is decreased by the same amount. So the resultant force is equal to kx minus kx, which ends up giving you F equals 2kx. Part III, state and explain the effect, if any, of increasing the initial displacement on the period of the subsequent motion. So no effect, as time period only depends on the length of the springs or the pendulum bob, as the system is isochronous. Part B. We've been given masses which are added to the glider and the measurement of 20t repeated. We have been given the results, and then we have to describe two different errors in the table. So if you observe, one thing that instantly stands out is these two values. Okay, so we can see, in fact, not all the values are rounded to the correct significant figure. Okay, so that's number one. And number two is that they haven't recorded the units of t or t squared in the table. So that's also going to be my second point. For the next part, we have to plot the first data point from the table on the graph below, and then the other points have been all plotted. The table of results is repeated on the opposite page, and include on your graph a line of best fit. Lovely. So we have, for the first value, it is 0.372. So that will be my value, and I just have to go ahead and plot the graph. So, okay, there we are. So let's do the next one, where you have to determine the value of k using the graph. So if you look back at the equation, well, k is given by that. So I'm just going to put that across here. So t squared is 2 pi squared m over k. And so if I just rearrange it, I know that k is 2 pi squared m over t squared, which is basically 1 over the gradient. Okay, so 2 pi squared over the gradient. And I'm just going to work out the gradient now. So the gradient is going to be 1 minus 0.12 over the change in x-axis, which is 0.7, and that will give me 1.257 seconds squared per kilogram, and I'm just going to put that in, which will give me an answer of 15.7 newtons per meter. Part C says, when the initial displacement is increased, one spring increases its extension whilst the other extension decreases. Explain why the maximum kinetic energy of the motion increases. So for this, I think let's look at some relationships. So we know that the kinetic energy is given by the total energy minus the potential energy. Or we can say that EK is equal to half K A squared minus half K X squared. Now, as one spring is extended and the other compresses, the EP value is going to increase. So the total energy will also increase. Now, we know that at equilibrium, the kinetic energy is maximum as the EP value is minimum because X is 0. There is no extension. Now, that means that as EP minimum is unchanged, okay, the kinetic energy value will increase with ET. And we know that Vmax is equal to omega A, and omega is constant. So Vmax is proportional to the amplitude. So if amplitude increases, Vmax increases, and therefore the kinetic energy, the maximum kinetic energy, also increases. I hope that makes sense. Okay, question number 22. We're given that a star has a mass similar to that of the Sun. Describe how the position of the star on a HR diagram changes as it evolves. And we've been given a blank HR diagram, and you may add information to figure 22.1 as a part of your response. And figure 22.2 shows the relative intensities of different wavelengths of light in the spectrum of a star. Explain how information from figure 22.2 could be used to suggest the stage of evolution of the star and describe the limitations of the analysis. So let's just focus on the HR diagram first. For a star that has a mass similar to that of our own star. So for that, we have obviously the main sequence, which is just a band in the middle over here. So main sequence. And then we have, and our sun is somewhere here. And then we have the red giants somewhere around here. So red giants, followed by red supergiants, which are slightly above over here. Super giants. And then we have the dwarf. So I'm going to link that evolution to explain how it goes about its cycle in terms of temperature and luminosity as well. And we are given a graph of wavelength and relative intensity. And basically, let's talk about how the star is going to evolve first, and then we'll talk about the limitations. So when a protostar in a nebula begins fusing, it becomes a star and initially appears in the bottom right of the HR diagram due to its low temperature and luminosity. As it burns hydrogen, it moves towards the sun's position on the diagram. And once all the hydrogen is fused, the core collapses and the outer layers expand and cool, forming a red giant. Now, the radiation pressure from fusion and shock waves during collapse causes this change. And the star's surface area will now increase, boosting the luminosity and shifting it upwards and to the right on the diagram. And eventually, the outer layers will drift off as planetary nebula, leaving behind a blue dwarf that cools down into a black dwarf. And the core collapses until electron degeneracy pressure balances gravity. Its small surface area results in low luminosity, but high temperature due to gravitational compression, moving it to the bottom left of the diagram in the white dwarf region. So using Wayne's displacement law, a star's temperature can determine its x coordinate on the HR diagram. However, without really knowing the surface area, luminosity is unknown. So that is one of the drawbacks or limitations of this particular in this particular question. So it makes it harder to distinguish, for example, a white dwarf from a high luminosity main sequence star with the same temperature. Question number 23. The Hipparcos Space Telescope used stellar parallax with a precision of 9.7 times 10 to the minus 4 arc seconds to determine the distance to stars. One of the stars studied was Polaris A, and we've been given the data about this star. Estimate the maximum stellar distance in parsecs that could be measured using this telescope. So we know the formula D equals 1 over P. We are given the arc seconds, so just stick it in the formula and we end up getting 1,000 parsec. Calculate the percentage uncertainty in the calculated value and the distance of Polaris A. So they have a parallax angle of 7.5 times 10 to the minus 3. So we can simply work it out by doing 9.7 times 10 to the minus 4 over 7.5 times 10 to the minus 3 times by 100. So that's 13% uncertainty. Part B says a continuous stream of particles called a solar wind flows from the surface of the star into the surrounding space. These particles include helium nuclei of mass 6.6 times 10 to the minus 27 kilograms. Assume that the atmosphere is modeled as an ideal gas. Show that the typical kinetic energy of helium nucleus in the atmosphere is about this much. So we know that the kinetic energy is equal to 3 over 2 kT. And so for that, it'll be 3 over 2 times Boltzmann constant 1.38 times 10 to the power of minus 23 times by the temperature, which is in Kelvins already. So 4 times 10 to the 6, and that gives me 8.3 times 10 to the minus 17. And if you were to, 17, and that could be rounded to about 10 times 10 to the minus 17. So that basically becomes 10 to the minus 16, roughly. Okay, so part II says the gravitational potential energy of a helium nucleus in the outer layers of the star is minus 2.3 times 10 to the minus 16. Calculate the gravitational potential energy U at the maximum distance from the star that a helium nuclei could reach. Okay, so we know that this is at the outer layer, times 10 to the minus 16. And then we have gravitational energy of the 8.3 times 10 to the minus 17 that we just worked out. And that would be minus 8.3 times 10 to the minus 17. In other words, it will be minus 1.5 times 10 to the power of minus 16 joules. Calculate the distance from the center of the star reached by this helium nucleus. So we know the potential energy, Eg, is given by minus gmm over r, and therefore r is equal to minus 6.67 times 10 to the minus 11 times by the mass of the star, which we need to go back to 1.1 times 10 to the 31, and times by the mass of the helium, which is 6.6 times 10 to the minus 27, over the potential energy that we just worked out, which is minus 1.5 times 10 to the minus 16 joules, and that gives me a distance of 3.2 times 10 to the 10 meters. Okay, last question of this paper. We have to explain why the star has a solar wind that reaches a much greater distance from the star than found in part III. Well, that's because not all the particles will have the same energy. Okay, so this is it, guys. I hope you found this paper useful. I'll see you in the next one. Thanks ever so much for watching.